As he said, my name is Miguel I come from DTU Photonic in the Metro Access and Short Range Systems group. And together with Roberto Rodes, TAM, and the group leader, Ildefonso Tafur-Monroy, we have written a paper entitled Real-Time Algorithm Temperature Compensation for Tunable Lace pixel-based WDM-PON systems. To explain what this is about, I would like to read that title again, only now backwards. So we are considering a WDM-PON system here. That means this is the scenario. We have a central office, a transport fiber, a remote node with split wavelengths for the different ONUs. And the main difference in this kind of architecture is that each ONU gets a whole wavelength for themselves. Actually, in the system that we are considering, each ONU gets two wavelengths, one for the uplink and one for the downlink. In the uplink, we are going to use tunable lasers at the ONUs. In the downlink, we are going to use pixels. This is how we have based our WDM-PON system. The problem with these laser sources is that they are not famous by their stability. And the problem that we are addressing in this presentation is temperature compensation, especially in ONUs. Tunable laser might get out of the channel, but also the remote nodes might also shift all of the channels, which leaves the link completely uncommunicated. Our solution to that problem is based on a real-time algorithm that is centralized in the central office and controls all of the ONUs and the central office. So before getting to know how this algorithm is made, I would like to talk about why we did that kind of project. And well, in a conference like that, I think everybody knows this figure. Thank you for everybody knows this figure, and basically what it says is we are now in 2012. We consume roughly 1 exabyte per month. And in only 4 years, in 2016, we are going to be consuming 10. So that's 10 times more in only 4 years. And I mean, well, yeah, we get it. We have new apps for streaming music and movies. We have new HTML standards that lets you play games on the web. We have super duper smartphones that can do everything. And we demand more bandwidth. The end user is demanding more bandwidth, and it's exponentially increasing. Fortunately, there was a couple of guys who came up who saw this problem and came up with a project which is called GigaWaM to address this problem and give a solution. GigaWaM stands for Gigabit Access Passive Optical Network using wavelength division multiplexing. Its goals are twofold: to create an access network that is capable of giving to the end user 1.25 gigabits per second, both up and downlink, and to do it without draining the end user, because that kind of system is really costly as of now. So the first one, we do it by employing a WDM-PON architecture to give to the end user two wavelengths for themselves. This is the main difference with TDM approaches. And the second one we achieve by something called hybridization, which is getting the optics and the electronics all integrated and compact in one place. For example, this is the central office for a 64 channel WDM-PON system. If we take a look closer, we can see that this planar light wave circuit, PLC, has already LC filters to divide the uplink and the downlink, because the pixels are emitting our L-band pixel and the tunable laser are C-band. It has also AWG 50 GHz per channel, which gives 64 channels in total. It has it's bidirectional. It was both directions because it has mirrors that direct the uplink upward so that they can be picked by photodiodes that are directly glued into the PLC. And using the same approach, we can glue pixels into the end facet section. And this is what pixels come really in handy, because the way they are fabricated, they can be made in an array, and the array and the spacing between the pixels can be made so that it matches the spacing between the waveguides in the PLC. And also, pixels are well known for their higher yield, which also reduces cost, and it's one of the goals of this project. If you want to know how a central office looks like nowadays, that's what you would kind of expect. So, at the ONU side, we are considering a modulated creating wide branch laser with monolithically integrated silicon optical amplifier, which has the back reflector is split into two cavities, the left reflector and the right reflector. This all goes into a multimode interferometer. It also has a phase section to fine-tune the wavelength again, and the SOA for the modulation. And that's a tunable laser, by the way. It all looks like this. It's really, really tiny, and it's integrated with the electronics. So why did we use tunable lasers for this experiment? Well, keeping in mind that one of the goals of the project is to reduce costs, one of the things that we would like to have is ONUs that do not depend on the channel they are hooked up. Right? If we have a fixed tunable laser with a fixed wavelength, and the end user happens to break the ONU, well, the operator would have to produce a specialized, customized ONU for that user. And we don't want that. We want users to go to MediaMarkt and buy their ONUs and plug it in their homes and work with it. So now we know we go to how we did that, right? We have pixels, we have tunable lasers, but we have temperature drifts, especially of the ONUs, and we want to have some degree of reliability in our system. So this is the setup I'm considering. Here's the central office, the remote node, and the ONUs. The central office consists of a pixel array and a photodiode array, LC filters, and the AWG. The pixels are controlled by a control board, which is connected to a computer, and the ONUs are also, tunable lasers are connected to another driver board, also connected to a central computer, which is located at the central office. Worth saying that the tunable laser has a built-in thermostat for reading temperature. In case of the pixels, we don't need temperature information, as I will explain shortly. So first, I will explain how the algorithm for the ONU works, and secondly, I will explain how the algorithm for the OLT, also central office, at the central office works. So we start with the ONU. Back to this diagram of how the laser is. The most important parameters for the wavelength here are the current that goes to the left reflector, the current that goes to the right reflector, and the current that goes to the phase. These three combinations of currents are we are going to call tuning lines, and each tuning line is going to give us a different wavelength. Now, not all combinations of currents give a stable tuning line, a stable wavelength, a single mode output wavelength. This is tested at the fabricator of this tunable laser, which is Syntune, and they run different combination of currents, and they give us the tuning lines that outputs a stable single mode wavelength. This is how it would look in a graph if we put several tuning lines together. And what you can see is that mainly you fix the left and right reflectors, and then you sweep the phase section from 0 to 12 milliamps, and this gives us a smooth shift in the wavelength. If you put all of the tunable lines together, this is what you get. This is some sort of interesting figure. What's happening here is that when you drastically change the left and right reflector currents, the wavelength jumps by a greater degree of nanometers. And then when you shift the phase section, then it smoothly shifts. That's why we observe these jumps. Hopefully we can see that each of the tuning sets overlap with each other. We're going to call each of those straight line tuning sets. So when we want to set a wavelength in our tunable lasers, we read the wavelength that we want to set, and we check for the tuning set with the central wavelength that is closer to that wavelength. And once we find this tuning set, we fine tune it using the phase section of the tunable laser. Also worth noticing that the C-band is completely covered by this tunable laser, which is good because we are using C-band for the uplink. Another interesting thing to say here is that these tuning lines are taken at different temperatures, namely 30, 40, 50, 60, and 70 degrees. So that we can have tuning lines characterized with different wavelengths for all of these temperatures. And this is what we're going to use to do temperature compensation. So now, how does the algorithm for temperature compensation work? Imagine we want to emit light in channel 4. And so we go to our tuning lines, we find our tuning sets with the central wavelength closer to the wavelength that matches channel 4, and then we fine tune. But it so happens that the ONU is 3.4 degrees away from when the tuning line was taken, say 34.4 degrees, and the tuning line was taken at 30 degrees. That causes the tunnel laser to fall out of the channel and go into channel 5, which not only loses your own connection, but also disturbs the neighbor. So what the algorithm is simply purposely tune the wavelength of the tunnel laser away from that channel, so that with the temperature shift it would fall in channel 4. This is a live demonstration of the algorithm working. We're going to say that we're going to change the temperature from 48 to 50 degrees, and we're going to see how the algorithm keeps the wavelength on the same place by purposely setting the wavelength that gives the tunnel laser away. Here's the program with the algorithm working, and we can see that the optimum currents would be here, but we are purposely setting currents away from there so that the output wavelength would fall in the right one. So this is the principle of working, and this is the demonstration that it can be used for working, for a real case scenario. Of course, in a conference like this, we would like to see some data, some measurable, accurate data, and therefore I decided to plot this graph. This goes from 30 degrees to 70 degrees. So the tuning is swept all over the place. This is what happens when the shift is not on. This is what happens when the tunable laser is set currents, and then we change the temperature without compensating for temperature. We can see that the wavelength matches the channel that we want only at the temperatures in which tuning lines were taken. If we compensate for temperature, then we get a graph like that, which is of course not perfect, but at least it's able to keep the channel within, to keep the wavelength within the channel during the whole swim. Also, there are difficulties in obtaining this data, because the power of the tunnel laser reduces with increasing the temperature, and also the way we had it set up, we had bad coupling to the tunnel laser, and then the coupling would simply drift as the temperature drifts. So it was quite difficult to obtain this graph, but I'm very proud of it. Let's go back to the central office algorithm. In the central office is much simpler. We have a pixel which has a bias current, and with the bias current you control the wavelength. And the algorithm, what it does is it sweeps. It's connected to a power meter down at the ONU. It receives feedback from the ONU, and it uses that feedback to maximize the power that it receives. And with this function, it finds the bias at which the pixel is emitting in the correct channel. So what it does, it sweeps, and whenever it finds a peak, it changes and reduces the step side, and does it all the time. Here's another video demonstrating its functioning. We start the algorithm, and we can see it sweeping until it matches it finds the optimum bias at which the wavelength is the correct one for the channel. This is what happens when you see it in OSA. When you run the algorithm, it's connected to this power meter, which is after the AWG, and then the algorithm is able to find the channel, because it sweeps all over the channels, and whenever it finds it, it sticks to it. Also, it's able to detect whether the channel is shifting in case of it's able to detect whether we have changed the channel. If it detects that the power drops drastically, and then the algorithm resets itself and starts finding the new channel, as we can see here. And also, we can purposely heat up the AWG so that all of the channels shift with the temperature, and the algorithm is able to detect that it has fallen below some certain threshold, and it would smoothly track the channel instead of resetting and starting all over. So here we are heating the AWG, and we can see how the algorithm is fine-tuning the pixel. so that we don't lose the connection at the ONU, the downstream. In a more accurate data, we can see how the algorithm converges to the optimum point, and you can observe that in the upper part of this graph you have the optical power received by the ONU. In the bottom side of the graph you have the bias that is being output to the pixel. Whenever it detects a peak, it changes the direction of the bias strip and it reduces the step size, and it does it until it converges, and we can see that it takes around 17 seconds to converge. All these results, I must mention, they were taken back in March, and we now have updated results with data information as well, and modulated data, I mean, in the channels, and it will be published shortly. So, concluding this work, we have realized a WDM-PON for access networks with all of its advantages, which is we have it fast, it's more secure because we give a wavelength to each of the users, and of course you increase the power budget. This is one of the main advantages also in WDM-PON systems. We have done it cost effective. In fact, the estimated price per channel is 120 euros, and we have done that by having a hybridization and having integrated electronics with optics. We have done it by choosing reducing operational cost at the ONUs by having a tunable laser, and we have grouped the two of them by having a centralized system in the central office that controls the temperature both at the ONU and at the central office. I would like to thank GigaWaM and the European Commission for money, Bertelas for the pixels, Syntium for the tunable laser, Ignis for the central office, for the AWGs, and you for listening.
Thank you very much for your presentation.
Mm-hmm.
Do you have questions?
Can I have a question?
Of course.
Well, right now you say you got results with the modulated data. Can you tell us about the bitrate, the
Yes.
modulation format, and so on?
For the pixels, we can modulate them all the way up to 2.5 gigabits per second.
Mm-hmm.
And for the tunable lasers, we can modulate it up to 1.5 gigabits per second.
Mm-hmm.
So this is well beyond the minimum requirement of the project, which is 1.25 gigabits per second.
Mm-hmm.
And we have to keep in mind that it's both for uplink and downstream. We have done similar recordings with the eye diagram,
Mm-hmm.
showing and seeing how the eye diagram keeps being there and doesn't disturb itself when the temperature is changing all over the place.
Mm-hmm.
Did you did also some bit rate measurements for this kind of? You say you were looking on the eye diagram. Did you did some bit rate measurements? Is it possible in this real time, or it's not possible?
We have it planned to do bit error measurements, although I fear that when the wavelength of the tunable laser changes drastically, most of the parameters of the eye diagram change, such as the extinction ratio and the average power, etc. So maybe it will be a little more difficult to get real-time bit rate measurements on this, and further research should be done on how to optimize the receiver to adjust itself to these impairments.
And is it sensitive to noise? Like if the front-end AWG introduces like
Well, right now in this PLC that I've shown there, we are having some 10 dB losses. And this accounts for the coupling losses and the AWG losses and C-band filters losses. And well, it does introduce noise, but it's not an active component. So the noise that it introduces is mainly because we are reducing the SNR by 10 dB.
Okay. And such an ONU, what you built, how complex is it and how much power does it consume approximately?
That's an interesting
Or is
question.
it like this, or like it's a chip, or it's
It is cheap, but the ONU is it has the optical part, and it is wire bound to all the electronics.
Mm-hmm.
And The complexity is not too high. I think it's rather simple. It's because the most complex part is done by the manufacturer of the tunable laser, which is Syntune, and they have done it with a very low cost profile and optimized for mass production. So, in my opinion, I don't think it's too complex compared to other schemes. I think it's a good approach.
Okay, thank you. So, is there our speaker here?